Okay, so let's see how we can use neural networks for classification. And I think this is going to be straightforward for you because you have already done your programming assignment one, where the job was to train a classifier on MNIST, right? So it's just like we'll try to cover all those details in case you have missed anything. Now, classification, we have covered this. It's just like trying to separate different data points into different categories. Okay, and even SVM, we saw that we need like some kind of machine learning framework which we can represent as a function which will take your data points and categorize that data point. So in case of k nearest neighbor, it was just like that distance function. In case of SVM, this was like that hyperplane which you were optimizing. Now, in case of your neural network, it will be like either your fully connected layer, or if you don't want to extract features, you want to like also learn features, it will be a CNN architecture. But the overall idea will be the same. You need a function where you will send in like either your images or your image features to make the prediction. Okay, and most of the times what you will have is you will have like a set of training samples which you call your training data, for which you need your annotations. Like for each sample, you should know like which class the sample belongs to. And then in case of nearest neighbor, you don't actually train that network. You just use like this label to propagate, like if the distance is like very close, then you just propagate these labels. In case of SVM, the training is like the optimization process. You have to find that hyperplane, and in neural network and CNN, you'll have to properly train it using again optimizer, where you have to find all the parameters in your network. Okay. Now, so that's the training process. Now, there are two variations in neural network. The first is you take your training images and perform some kind of feature extraction, right? And then use those features to train your neural network. That's like strategy number one. The other strategy will be you directly use your images and you don't have to extract your features from each of these samples. So your CNN network will extract those features for you, and then you can train your network and make the predictions. And the benefit of that is that, so when you're extracting your features beforehand for your neural networks, then you're kind of using some kind of domain knowledge, right? So you have to assume that whatever features you're extracting, they are actually relevant to or important for this classification task. So for example, if you're using, let's say, histogram of gradients, then you should be confident enough that, okay, so edges are important to classify these kind of images. So that's like assumption you'll have to make, and it might happen that the features you're extracting, they are not useful for classification. So that's like a big drawback. So just to give you an example, for example, let's say you are using just the color information in your images. Okay, and you have to, let's say, perform action classification, determining which action is happening in this image or in this video. So in that particular case, color is not going to help you, right? So like how sophisticated features, you can extract like many sophisticated features using colors as well, but at the end, those features are not going to help you when you're training your classifier. So that's a big drawback. Now, in case of CNNs, what you're doing is you're directly sending in your images to extract the features. So when you're training your classifier, then the loss which the classifier is getting from like the final whatever objective you have, then that loss is also used in like that gradient descent algorithm to learn the kernels which are used to extract the features from images, right? So that's called end-to-end learning. And then what's happening is, if colors are not important to perform this kind of classification task, then the kernels will never extract the color information. Okay? So the kernels, or whatever parameters you have, only those features will be extracted which are meaningful to perform that particular task. So that's like that's very important in your CNNs, and that's like what makes them very powerful. So that's why like end-to-end learning is really important. It's not just classification. It's like whatever task you're doing, whether it's like object detection, segmentation. So what will happen is if your network is end-to-end, you are learning like it all together, like both feature extraction and classification, then you will extract only those features which are relevant to the task at hand. Now, if you want to extract your features beforehand, so these are all the variations, and I think we have covered most of these. Raw pixels, that's fine. It's just using the pixel values. We have histograms, then SIFT, HOG. SIFT we didn't cover, but it's like an advanced version of SIFT. And then the final is like, what about learning these features? Okay, that we will see like in CNNs. Now, for neural networks, these are like fully connected layers, all right? So you will have to input the extracted features, and then you will have certain dimension of in the features, right? So each of the neuron will belong to like each of that dimension, and this is like a standard neural network. So we'll have certain layers. In this case, we have just one hidden layer, but you can have multiple layers. And the decision you have to make is like how many layers you want, how many neurons you want to use. So the first input layer you can easily determine using like what kind of features you have versus dimensionality of that feature. The final output layer you can easily determine based on the classification problem. So if it's a binary classification, then you can either predict like just one output or two. But if it's a n-way classification, you'll have to predict n different probabilities. And intermediately, like you can determine based on how complex your problem is, you can increase like the number of neurons or the number of layers. Okay, so the important thing to note here is that the input is the extracted features, not the images. And contrast to this, in the CNN architecture, the input will be the data itself. It will be like the input image, or it could be like the video itself. And this is like the general architecture of your CNN. You will have certain convolution layers. Then you will have subsampling or max pooling in between to reduce the shape of your feature maps. And at the end, so this is like your feature extraction stage. You'll have to just flatten those features. So that will be your extracted feature. And after that, you will have the fully connected layer similar to this. Okay. Now, neural network, I think we talked about this when we were covering the basics of neural network. So one neuron is, it will have certain inputs, and it will try to combine all these inputs to make some kind of prediction. And this is like the basic building block. And then you combine several of these neurons to construct like a bigger neural network. Now for multiple classes, what you will do is you don't have to change your network much. It's just like you'll have to modify your output layer. And based on the number of classes you have, you will have to make that many predictions. Okay, so that's the only difference between your binary classification and multi-class classification. And I think this composition, we also studied like how we can have multiple layers so that have composition between these functions. But the interesting thing there was, if you don't have like non-linear activations in between, then it doesn't matter like how many layers you have. It will again be like reduced to just one function. It will just a linear combination of your inputs. So we will see that later, how to use those activations. Now, for CNN architecture, we covered this AlexNet, which was used for ImageNet classification. And there are like some general guidelines which I think you can use when you are designing your CNN architecture. So let me quickly go through them. So you'll have your input image, and then you'll have to define like how many kernels you want to use to extract features or low-level features from your image, right? So in this case, we are using 96 different kernels, right? And so the other parameter is like you have to define like the shape of your kernel. And in this case, it was 11 cross 11, but we don't use like these bigger kernels anymore. We either use like 3 cross 3 or 5 cross 5 kernels, because at like a low level, we are just trying to extract like very basic features, whether there is an edge, whether there is a curve or not. Okay, so one general guideline is you use like fewer kernels at the beginning, and you start increasing the number of kernels you have, and then again try to reduce the number of kernels. Okay, so the basic intuition behind that is when you are extracting features from your input data, usually it will have a very high resolution. Okay, so in this case, it's 224 cross 224. So one reason why you need fewer kernels is that irrespective of which class your image belongs to, the basic structure or the basic features, they will be shared like among different classes, right? So for example, in almost all the classes, you might find like vertical edges, you might find horizontal edges. So these basic shapes or these structures, they are shared among multiple classes. So you don't want to use too many channels, because then that will be like extracting too many low-level features which are not actually required. Okay, so that's like one intuition. The second intuition is in your first layer, since your resolution is high in your input image or your input video, the size of the feature map or this volume, it will be huge, right? So you want to like save some memory as well. So for example, if you have using like, let's say 384 channels in this particular case, so that's like a lot of features if you do the math. So it's not like memory efficient to use a lot of channels. So those are like just two intuitions. And then later in the network, what will happen is you are going to use max pooling, right? Then the shape of like your feature map is going to reduce, and then you can like try to expand your number of channels to compensate that, and that will allow, that will ensure that you're not using too much memory. All right. So that's one thing. The other is the other intuition is as you go deeper, then so these the first initial layers were trying to extract like basic structures, right? But as you go deeper, then you're starting to like extract complex structures. And if you compare complex structures with like your basic structures, you will have way more complex structures than basic, right? Because complex structures are nothing but like combination of basic structures. So let's say if you have 100 basic structures, then using those structures, you can come up with like much more complex structures, right? So that's kind of another intuition why you should like increase your number of channels. And at the end, the idea is you are trying to extract like very complex, not complex, these are like, you're trying to extract like the object itself. So if you're, let's say, trying to classify a basketball, then at this level, the feature map should already know whether a basketball is present or not. Now, you don't have like too many object categories, right? So that's like one intuition. So for example, if you're using a 10-way classification data set, then you have only 10 classes. So you don't want to use too many channels in this case either. So that's not always true, but it kind of like applies to most of the cases. So that's reason number one why you reduce the number of channels. The other reason is, so when you're reaching towards the end of your network, then ideally, and again, so this used to happen, but we have a different way to do it. But let's talk about this first. So what you do is you flatten your features. And we have seen this, like, I think in the programming assignment as well. So whatever features you have here, because from this point onwards, you will have to construct this classifier, right? Which has fully connected layers. So your fully connected layers only takes flattened features. It's like one-dimensional feature vector. So, and this is like a cuboid. So what you'll have to do is you'll have to flatten this. Each pixel or each feature value in this map will be like one dimension in the flattened version. So in this particular case, what will happen is if you flatten this cuboid, it will have 13 cross 13 cross 256 different neurons, and that will go into the next dense layer. Okay, so if you use too many channels, then what's going to happen is you will have too many neurons. And if you have too many neurons, then moving from one dense layer to the other dense layer will have too many parameters. So it's simply like number of neurons in this multiplied by number of neurons is in this one. So that's another reason why you don't want to have too many channels. But again, these are like some guidelines, and these might change depending upon like what kind of architecture you have. So let's see, I think there is a question from Furkan. Is the mask RCNN instance segmentation comes before the convolution? So first of all, we haven't talked about mask RCNN or instance segmentation yet. So I don't know why this question is relevant here, but still, if you're interested, I'm not sure if I get your question correctly. So let me read it out again. In the mask RCNN instance segmentation comes before the convolution. Yeah, I think we can discuss this later because I don't think this is like in scope of what we are discussing right now. Instance segmentation comes before convolution. Yeah, I didn't get your question. Anyways, we can discuss that later. Okay, so then you will have some fully connected layers. And this is like similar to the neural network architecture, which we discussed. Finally, we'll have to make a prediction of, in this case, there were 1,000 classes. So you will have 1,000 different predictions. So these are like some general guidelines, I think, which you will find useful when you design your own network so that you don't make like those mistakes. Okay. Now, another interesting point, as I said before, that let's say if we don't want to perform that feature flattening, and can we just have a fully convolutional neural network where we don't need that classifier at the end, right? So we just want a convolution layer. All layers should be convolutional, and we can make the prediction, and that's totally possible. And we have some variations like that for classification as well. So let's see how that can be done. So let's quickly go through like some points here. First of all, we don't need any feature flattening. We don't need any fully connected layers. Now the trick is we want to reduce the spatial dimension to 1 cross 1. Okay, and let me go back quickly. So in this case, the spatial dimension is 13 cross 13. So what you want to do is you want to perform some more convolutions, or maybe perform some max pooling operations before these layers, so that the shape of this feature map is 1 cross 1 cross 256. All right. And then what we can do is we can simply use a 1 cross 1 convolution for the prediction. And in a way, like this 1 cross 1 convolution is also a fully connected layer. Let me explain why. So once you have this 1 cross 1 cross 256, if you apply a 1 cross 1 convolution after that, so if you remember like from the CNN lecture, the third dimension of your kernel, it will automatically match like to the depth, right? So when you're saying 1 cross 1 convolution, the actual shape of that kernel is 1 cross 1 cross 256. So in this case, what will happen is you are just taking linear combinations of these 256 values. So these 256 values are your features, and applying a 1 cross 1 convolution is exactly same as applying a dense layer, right? So when we apply one convolution kernel, so if you remember the equation of convolution, it will be just a linear combination of these, right? And this will give you one value. If you apply another convolution kernel, that will again be a linear combination of these, will give you another value. So if you need 1,000 values, You just need 1,000 different kernels, and those will be like linear combination of the same set of values. And it's exactly same as this final fully connected layer, because in that case as well, each neuron is just a linear combination of your feature vector. Okay. So another question from Saeed, do we still use activation functions after a convolution layer? Yeah, we do use activation function after a convolution layer. And again, I mean, I must warn you, I think I have seen like a recent research paper this year, which try to prove that even if you don't use any activation function, we can still get like the same set of results when we are using activation functions. So that's like a kind of ongoing research, just to give you like an idea. But yeah, traditionally we do use the activations after your convolution layer. So 1 cross 1 cross 256. Yeah, so you can apply activation after that. Okay. So let me see what else I have. So yeah, this is just trying to explain. Okay, so we still have time. So this is like your traditional CNN. Okay, input, you have these feature maps, you flatten these, and then fully connected layers, and you predict 4 neurons. Now, what you do is, so these two are exactly same, these two are exactly same, but instead of flattening this and turning this to like 400 neurons, what you do is you apply a 5 cross 5 kernel on top of this, and that will just give you one value for each location, right? And you have apply like 400 different kernels. That will be like a 1 cross 1 feature map, right? So then what you can do is just apply more kernels and you can make the prediction. Okay, so okay, let me see what happened just here. 5. Okay, so yeah, I think so this is fine. I think there was a question, what is the advantage of conv versus fully connected? Is it faster? So it depends on like how you are designing your architecture, right? Because as I said earlier, your exactly the same set of operation. So when you are moving from this layer to this layer, compared to this, it's the same operation happening, right? So this neuron will have a value which is going to be a linear combination of all these neurons, right? Similarly, what will happen is one value or one neuron here will be a linear combination of all these neurons. And similarly, like the second one will be again the same. So it's the same operation, and but it depends on like how you are. So for example, in this case, if we directly flatten this, so you can see that in this case, you have one additional operation here, right? So this flattening is not taking any time. It's just reshaping your feature map. So this is like, this will not count towards any computation cost. But in this case, you are performing this convolution operation on this feature map to reduce to this size. So in that sense, it's like, it's taking more computational steps. Okay. So another question from Gayur. In the last step, how do we go from 1 cross 1 cross 400 to 1 cross 1 cross 4? So you just apply a 1 cross 1 cross kernel, right? And you apply like 4 such kernels. So the first kernel will give you one value, The second will give the second value. All right. So if you think about this, this is exactly same as like this layer. I mean, there is no difference between these two. It's just like how you are interpreting. So I had a pop quiz here, but let's skip that. And because we are out of time, so let me see how. It's already 35. Let me see how many more slides do I have. Okay, there's a lot. Okay, let me try to cover until activation, and then I think we can cover the rest in the next lecture. So as we saw, like when we were doing neural networks, if you have multiple layers and if you don't use activation functions, specifically like non-linear activation functions, then you are not like making your networks better. It's just like same as like using one layer, because you can easily reduce those multiple layers to single layer, right? And again, it will be just a linear combination. And therefore, as we discussed earlier, we need activation functions. And these activation functions are like non-linear functions, which like allow your network to learn complex functions. So what you do is, so this is like a sigmoid activation function. And you can see that this is non-linear. And you should also know that whatever activation function you use, it will have to be differentiable, right? Because if you have to train your network, then you have to compute gradients, gradients to do backpropagation, right? And if it's not differentiable, then you will not be able to do that. So sigmoid activation function, what it will do is it will take like the output activation or one of the values from your feature maps and will scale that between 0 and 1. Okay, so that value can be anything. So this is like negative infinity and this is positive infinity. So it can be anything. What it will do is it will just scale it between 0 and 1. So if your output activation is 0, then it will be 0.5. If it's close to 4, then it will make it 1. And if it's like greater than 4, doesn't matter how big, it will still be close to 1. Okay, so that's how this sigmoid works. Now, one interesting thing about sigmoid is you'll have to apply this activation independently on each activations, right? Or each like feature values. So it doesn't have like any relation between how you're applying this to other or other activations in the same feature map. So it will have to be independent. It's just scaling each and every value between 0 and 1. So similarly, we have other activation functions, and all of these are also applied like independent of like what you're doing with other pixel values. And so sigmoid is like when you scale between 0 and 1, and tanh is like when you're scaling between -1 and +1. And ReLU is a bit different, where you just clip your values, you just ignore negative values and keep whatever you have as positive. So one big advantage of ReLU is if you want to find a derivative, it's pretty simple, right? It's a straight line. But if you have to compute a derivative for these functions, it's computationally expensive. So in that terms, it's faster to train networks when you're using ReLU activations. Now, so one use is like to learn nonlinear decision boundaries, right? To make your networks nonlinear or learn complex functions. Another interesting use of activation functions, I think someone asked a question when we were talking about how we can define fully connected layers, fully convolutional neural networks instead of using fully connected layers. So we can also use activation functions to make sure that whatever values we are predicting, they are in certain range. And let's talk about like some scenarios where they are useful. So for example, if you are doing classification, right? So classification means you will say whether this class is present or this class is not present. So which means that either the target values will be 0 or the target values will be 1. So in that case, if you apply a sigmoid on your predictions, because the network will predict arbitrary numbers, right? Because what it does is it takes the input feature maps, and when you apply convolution or a fully connected layer, it's just a linear combination. And depending upon what weights you will have in your fully connected layer or in your kernel, you can get arbitrary like small or large values. So just to keep them in range, you can use sigmoid and make sure that your values are between 0 and 1. Similarly, if let's say you are solving a regression problem where let's say you are doing image synthesis, right? Ideally, your image, the pixel values are between 0 to 255. But what you do is you usually normalize that value between either 0 to 1, or you can also normalize between -1 to 1, right? So then if that's the case, then whatever when you're trying to synthesize your image, then your values should be in that range. So then tanh is pretty useful, okay? So that's fine. So again, if your target range is between 0 and infinity, it again can be a regression problem, then ReLU might be useful. Okay, so I think we should stop here. We are almost out of time. And I think if you have any questions, we can cover those.